Welcome back to The Explainer. Today, we're pulling back the curtain on organic chemistry to reveal the surprisingly simple blueprints that chemists use to, well, build pretty much everything around us.
Have you ever looked at a really complex molecule, maybe for a life-saving drug or some high-tech material, and just thought, how on earth did anyone figure out how to make that? It can seem almost impossibly complicated.
But here's the thing. It's not magic, and it's definitely not about memorizing thousands of different reactions. Almost the entire vast world of organic chemistry boils down to just a few basic, fundamental patterns for how chemical bonds are made and broken. Okay, so let's get right into it. If you want to understand what's happening in any chemical reaction, there is one single question that you have to ask first. It's the key that unlocks the whole thing.
This right here is the chemist's golden rule. If you can just figure out which bonds are disappearing and which new ones are showing up, you can basically follow the plot of any reaction. It's your first step to seeing the logic behind all the chemistry.
And here's the best part. That golden rule doesn't play out in a million different ways. Nope, it really only shows up in a few core repeating patterns. You can think of them like master blueprints for building molecules.
Believe it or not, something like 80% of all the organic reactions you'll ever see fall into one of these three main buckets. You've got addition, where you break a double bond to stick on two new things. Then there's substitution, which is pretty much what it sounds like. You just swap one piece for another. And finally, elimination, where you pull off two groups and form a new double bond. And if you look closely, you'll see addition and elimination are basically just opposites of each other.
So let's see how this actually works. We're going to zoom in on one of the most powerful blueprints of them all, the substitution reaction. And we'll see how chemists can use it to modify some of the most stable molecules that exist.
To do that, we first need to talk about a class of molecules called arenes. The most famous one is probably benzene. Now, these molecules have a ring of electrons that's, well, it's special. The electrons are shared across the entire ring, which makes the molecule incredibly stable. We call this special stability aromaticity.
So here's where it gets really cool. The arene is kind of at a crossroads. You might think, hey, it's got all those electrons and double bonds, it should be perfect for an addition reaction. But, and this is a huge but, doing that would actually break that super stable aromatic ring, and that costs a ton of energy. So, instead, it does something much smarter. It chooses to do a substitution, just swapping out a hydrogen for something new, because that lets it keep its precious aromatic stability completely intact. And this whole dance is called electrophilic aromatic substitution. It happens in three basic moves. First, the electron-rich arene uses its electrons to attack an electrophile, which is really just a fancy word for a molecule that's hungry for electrons. Second, this forms a temporary, kind of awkward, unstable structure. But then, in the final step, the molecule kicks out a hydrogen atom and snap, that super stable aromatic ring reforms, good as new, but now with a new group attached.
All right, so everything we've looked at so far involves electrons moving around in pairs. But you know what? That's only half the story. There's a totally different way bonds can break, and it opens up this whole other universe of chemistry. It's called homolytic cleavage. So instead of one atom grabbing both electrons from a bond, imagine the bond splitting perfectly, right down the middle. Each atom walks away with one electron, and what you're left with are two radicals. These are superreactive species that have a single unpaired electron just hanging out. And this slide right here perfectly shows the two parallel universes we're talking about. On one side, you've got your ionic reactions, where electrons always move in pairs, creating positive and negative charges. We show that with a normal double-barbed arrow. But on the other side, you have radical reactions. Here, it's single electrons that are on the move. And to show that, we use these really unique single-barbed arrows that chemists call fishhooks.
Now, the real power of these radicals gets unleashed in what's called a chain reaction. It all starts with initiation. You need a little spark of energy, maybe some lighter heat, to create the very first radicals. That kicks off the propagation phase, which is the self-sustaining engine of the whole process. This cycle just keeps going and going, churning out product, until you get to termination, which is when two radicals finally meet and combine, ending the chain.
Propagation is really where the magic happens. Check this out. In the first step, a radical gets used up to make a product. But then, in the second step, a new radical gets created, and it's the exact same type of radical that started the first step. It's this beautiful, self-perpetuating cycle. It means a single spark at the beginning can cause thousands and thousands of molecules to react before the chain ever stops. So we've gone through ionic substitutions and radical chains, but what's the big picture takeaway here? Why is it so game-changing to stop thinking about memorizing reactions and start thinking about spotting these patterns?
Well, here's the bottom line. Organic chemistry isn't some foreign language with a million words you have to memorize. It's a system with a clear logic and grammar. By always starting with that golden rule question and then recognizing if you're looking at an addition or a substitution or a radical reaction, you go way beyond just knowing what happened. You start to truly understand the how and the why.
It is pretty amazing when you stop and think about it. The same few simple rules are responsible for the molecules that make up life itself and the materials that have built our modern world. It just goes to show you that nature's incredible complexity is often built on a foundation of surprising, elegant simplicity. And that leaves you with one final thought. Now that we know the blueprints, what new things are we going to build next?